Hello everyone, this is Beibin from Microsoft. Today I want to introduce Whopper to efficiently adapt cardinality estimators for data and workload shifts. As we know, machine learning is popular for database systems in the last few years. In research, we use machine learning for cardinality estimation, index tuning, and graph partitioning. Also in practice, we have Oracle's HeatWave, Google's AlloyDB, and MIT's SageDB. However, recently researchers noticed some caveats in AI applications. One of the top challenges in AI application is the training and testing distribution shift. We know machine learning and data-driven models learn from historical data. When the historical data is not representative for the future, which means the distribution drifted, then the trained model might perform terribly in the future. In this study, we mainly focus on cardinality estimation because it is an important task for many downstream applications. Cardinality estimation is a task to estimate how many items are selected for a given query. We can usually iterate through the data table to get the ground truth cardinality, but it takes a long time. So researchers have designed many efficient approaches to estimate the cardinality. For instance, machine learning. For here, the machine learning approach tries to learn a function f by taking the input query x and then to output the ground truth cardinality y. Nevertheless, machine learning would face challenges when data shifted or workload shifted. During a data shift, users might insert, delete, and update the table. So for the same query, the cardinality might change. For instance, in the data table here, colored in orange, the cardinality was 2, but after the table inserts, we got 3. The workload distribution shift is slightly different. In this case, the data table will stay the same. However, the prior workloads are different from the future workloads. For instance, here, each row is a query, and the previous query usually have correlated weight and price. However, the workload drifted, and now the weight bound and price bound becomes inversely correlated. And the data shifts or workload shifts might lead to performance regression. For instance, we use a TPCH dataset, for example, and we want to join the order and line item type table. For the line item table, we have the machine learning based cardinality estimators. And the figure here shows the distribution before and after the shifts, where each dot represents one predicate. And the X, which is colored in blue, represent the previous distribution, and the X prime colored in orange represent the new distribution. We evaluate the geometric mean of Q arrow and the join latency, and the vertical red lines represent when the workload have shifted. And we notice that after the workload shifted, the GMQ arrow increased by 4 times, and the average latency for the join operation also increased by about 30%. Previously, in cardinality estimation, researchers either use retrain, fine-tune, or partially retrain to address the data or workload drift. In some other database tasks, researchers have used ad hoc methods with some domain insights to adapt data shifts. However, those methods are often overly general, and the data workload shift problem is understudied in machine learning for systems. We have 3 primary goals here to solve the data and workload shift problem. A good solution should be agnostic to the underlying machine learning model, and the method should also have small computational overhead. At last, it should adapt quickly. So we designed Whopper. It can adapt any black box cardinality estimators at the model M here. And it also contains a GAN design with a generator and discriminator to synthesize additional queries and workloads for the model to learn from. At last, it has a picker design to pick useful queries from the query pool for labeling and fine-tuning. And we will illustrate the Whopper example by using 3 different drift case examples below. In our first drift case, we have a workload distribution drift. In this case, the table stays the same and the workload changed. Here, each row represents 1 query, and we have lots of queries from the previous distribution. The first 2 columns represent bounding values in the query, and the green column here represents the ground truth cardinality. In the previous distribution, we noticed the weight range and price bound are linearly correlated. And now we detected workload shifts. and we only obtained a few queries from the new distribution where the weight and the price are negatively correlated. We found out because we only have a few queries, they are not enough to train or fine-tune the machine learning system. So the generative adversarial network, which is also known as GAN, inside our Whopper system becomes active. We take two sets of data as input to the generator, and the generator will synthesize data that is more similar to the new distribution rather than the previous one. In order to distinguish the different distributions, the discriminator takes a query as input and classifies the input query into three categories: the previous one, the new one, or the synthetic one. And you may already notice the GAN design in our system is slightly different from the traditional GANs because the discriminator needs to classify into three different categories. At last, we can label the ground truth for the synthetic queries and use the synthetic query as augmented data to further fine-tune or retrain the underlying cardinality estimator. We also use the pre-training strategy and the encoder-decoder design in both the generator and discriminator to save memory and runtime. So we performed several experiments with lightweight models and MSCM. 3 data sets are examined, and we assume there are 12 newly coming queries per minute. We evaluate different approaches in a stream setting. For here are the results, where the x-axis represents the time over the simulation, and the y represents the geometric mean of Q error, where the lower values are better. Each table here represents the results from one data set, where the red lines represent the naive fine-tuning method. The green lines represent hard example mining, where the data system will choose hard examples from the newly incoming distribution and weight them more during the training phase. The orange lines represent a mixture of distributions where it performs slightly better than the fine-tuning, but sometimes it will perform worse. And the blue lines represent the data augmentation method, which usually add Gaussian noise to the new distribution and enrich the training set. And at last, the purple lines represent our proposed Whopper system with a GAN to generate additional synthetic queries to further fine-tune the system. Compared to the naive fine-tuning, our Whopper system is about 3 times to 7 times faster to reduce half of the Q error in our experiments. In summary, in our drift case 1, we have workload drift, and the scenario is we only have a few new queries, and the small sample size are insufficient to train our model. And our goal is to adapt the black box machine learning model quickly, so we use GAN to synthesize additional queries. However, what if the number of new queries is large? This leads us to the next drift example. In the drift case 2, we have too many workloads to label. We also have the workload distribution shift, where the data table stays the same and the workload changed. The previous distribution is similar to the previous case, where I have lots of queries. And in the new distribution, we also have many different queries. The problem is we don't have the label for them. If we can find out useful examples among the unlabeled queries, we can label them first, which can provide more information to the machine learning system. However, the challenge here is we don't have the ground truth cardinality. How can we tell which queries are harder or more valuable with the ground truth cardinality? This brings us a picture in our Whopper design. We put all queries together into a container and record the source of the distribution. Then we perform encoding and clustering on those queries. In the example here, the red dot represents a query from the previous distribution, and the blue dot represents query from the new distribution. We reuse the components in the GAN with encoder-decoder design to project higher dimensional queries into lower dimensions for clustering. We notice the first cluster has more queries from the new distribution, so we select some unlabeled queries from this cluster for annotation. We also use stratified sampling here to balance exploration versus exploitation to add more varieties to the different clusters. At last, we label those selected queries and feed them into the black box cardinality estimator model. Our experiment shows that the proposed method, the picker, also outperforms naive fine-tuning with the same computation overhead. In this drift case, we also have workload shifts and the number of new queries is large. We select novel queries with higher priority for labeling. We notice both the drift case 1 and 2 are workload shifts, where the first example has a few queries and the CPU is in idle. The second example has lots of queries and the CPU cannot label all of them. Next, we will discuss the scenario when the table changed significantly. In the third drift case, we have a data table and a set of queries. The data shifted because users have changed the table, for instance, insertion, deletion, update. Hence, the previous cardinality ground truth becomes outdated. Suppose there is no workload shifts, which means the queries are almost identical, but we still need to recalculate the ground truth labels after the data shifts. The Whopper also solves this challenge with the picker design. As time goes by, we would know some errors from the newly labeled queries. Again, we perform encoding and clustering of those queries based on the errors. In the figure here, the blue dots represent unlabeled queries, large red dots represent known errors for some queries, and small red dots represent known queries with small errors. We perform sampling here based on known errors, whereas the cluster with higher average error, for instance, this one, has more probability to be selected for annotation. At last, we label the selected queries and use them to fine-tune the cardinality estimator. In this experiment, our proposed system also outperforms the baseline methods. From those drift cases, we can see the first drift case has too few queries. The second drift case has too many new queries. And the last drift case has a data shift. In the first two drift cases, we have workload drifts. We synthesize more queries with scan to help when new queries are scarce. In the last two drift cases, when too many queries need to be labeled, we use the picker to select useful queries. In practice, workload and data drifts can happen at the same time, and our Whopper system can also adapt those drifts at the same time by combining the GAN and the picker together. Other different drift examples and an end-to-end experiment with continuous drift are shown in the paper. Our work is related to active learning and a generative adversarial network. Our approach is inspired by both database communities and also the machine learning communities. In this study, we find out machine learning for systems also suffers from data and workload drifts. So we created a Whopper system to adapt drifts for cardinality estimation. It has low computation cost and outperforms other baselines in our experiments. Future studies can examine real-world workload and data table drifts in an end-to-end setting. Thank you so much.